Hello everyone, this is Mustafa here solving soil mechanics problems for civil engineering students. In this video I'm talking consolidation and this is question number 8. You can refer to my other videos for more problems. Let us see what we've got here. We are given a soil profile of clay that's 10 meter thick and it's one-way drainage because we have impermeable layer here. We are also given the coefficient of consolidation in the horizontal direction and in the vertical direction. The horizontal value is 14 meters square per year and the vertical value is 9.6. And also we are given that there will be a surcharge here, that's load, applied through an embankment in the presence of vertical sand drains, those ones here, to accelerate the consolidation by affecting radial drainage. We are also given here these curves for relationship between the degree of consolidation in the radial direction versus the time factor for the consolidation in the radial direction. Let us see what's required. So first, we are required to determine the time to 90% consolidation for the case with no drain. So forget about these vertical drains. We treat the clay as one deposit that will basically drain only in one direction. The maximum length of the drainage will be the full 10 meters here. And then the second requirement is to repeat the same problem to determine the time to 90% consolidation, but with these drains present. Solution strategy for problem of that nature is first, we apply the consolidation rate formula for vertical drainage. This is straightforward, we will see in a minute. And they then apply the consolidation rate again, but now for the combined effect of radial drainage, because when we have a water particle here, it will basically consolidate radially, but it can also travel vertically if the path is shorter. So we will have a combined effect between the vertical and the radial drainage. Essential knowledge. We need first to understand the concept of radial drainage. So we have here vertical sand drains in plan, these small circles in either a triangular pattern or a square pattern. The problem we have in hand is a square pattern, as we can see here. So that any soil element here will be able to consolidate both radially and vertically. We need also to understand how to apply the consolidation rate formula and obviously how to apply the consolidation rate formula for radial consolidation. Let us see how we can solve this problem. First, in the case of vertical drainage only without sand drain, so this is impermeable layer and the thickness of the clay given as 10 meters. So the longest drainage path for a water particle here will be the full thickness, which should 10 meters because it's only draining upward. The equation for the time to 90% consolidation, you should be very familiar with this. TV is the time factor, HD is the longest drainage path, CV is the coefficient of consolidation. Now we have the time factor is 0.848 given from this table here. As you can see, when the degree of consolidation is 90%, that's 0.9. The corresponding value for the time factor is 0.848. CV given 9.6. H is the longest drainage path is 10 meters. So now I can simply substitute in this equation to work out the time factor. Sorry, to work out the time T. Cut. To work out the time T. 0.848 time factor, 10 square, the longest drainage path, divided by 9.6, which is C sub V. So I have 8.8 years or 3,224 days, which means that in the absence of these sandy drains that can aid with radial consolidation, this clay will take 8.8 years to consolidate. Now let us see the effect of the radial drainage through the vertical sand drains. When we have radial drainage, so we will have combined radial and vertical consolidation. And this is the governing equation. U is the total or combined degree of consolidation. UV is the consolidation in the vertical direction, and UR is the consolidation in the radial direction. We are given that U equals 90%. So what we are missing here is the time. We don't know the degree of consolidation that will accompany this 90%, and we don't know the radial degree of consolidation also. The only way we can solve this problem is simply by trial and error, assume T, and then get UV and UR, substitute here to see whether we are fulfilling the requirement of U being 90%. Let us do this and see how we can calculate it. First, let us assume T equals 120 days. Remember, this is the equation we are after. The easiest part is to get the degree of consolidation in the vertical direction. So here I can simply substitute in this equation to get the time factor. CV is 9.6. Time assumed 120 days. You divide it by 365 days to be consistent in units, given that CV is given in years. Divided by h square, that's 10 square, and this has given me 0.031. I can substitute here now because I have TV, so I can calculate U square and then U. So this has given me the degree of consolidation that will be associated with 120 days combined consolidation is 19.8%. Let us see how we're going to get the radial degree of consolidation. Again, we have this equation here. That is the equation when the radial consolidation is solved. So CHT divided by 4R square. R is the radius of this virtual consolidation circle. And R small here, by the way, is the radius of the sanded drain itself. So I can substitute here. CH is 14, that's given. And I want you to note that normally the coefficient of consolidation in the horizontal direction is greater than in the vertical direction. Again, we substitute for T120 and we get 0.226. This is the time to use this graph. Now I need to get the degree of consolidation, vertical axis, that correspond to the coefficient or the time factor being 0.226. To do this, what I need to get is, you will have this on a piece of paper. So 1 log unit here with me makes 3.8 centimeter for the time factor changing between 0.001 or 0.01 or any other one full log unit. So 0.226, when you work out the log of this 0.226, it will come as minus 0.645. So it will be to the left of 1 here because log 1 is 0. So whatever after 1 will have a positive value for the log, and whatever before it will have a negative value. So I basically multiply this 3.8 centimeter by log 0.226, and then the distance would be 2.4 in this particular case. So I measure it, and then this will go and intersect this blue curve. What is this blue curve? This set of curves correspond to the ratio n of r capital, which is the radius of this virtual circle, divided by r small, which is the radius of the sanded drain itself, in our case being 0.3. Let us calculate this first. So r over rd is 0.564. This is the virtual radius as a function of the spacing, times 4 divided by 0.3, it's 7.5. So the first curve is 5, the second curve is 10. So I can draw by eye, obviously, the dashed blue curve here. So the point 226 will intersect this, and I can go to the left. This will give me the corresponding degree of consolidation in the horizontal direction. In this case, it is 0.8. I can now substitute here. I know the degree of consolidation in the vertical direction, 19.8%. I just plug it in here. U radial, you plug it in here, substitute to get U, so U will equal 0.836. I am after U, if you remember, 90% or 0.9, so this means 120 days is not the solution. So I can repeat the process again for other few values. For T, like in this table, 120 is what we tried here. I repeat it again for 140 days. The degree of consolidation is 0.866. Try it again for 180 days, say. You get UV, you get UR, you substitute in this equation, you get the corresponding U. You can see here that U.9 is somewhere in between. I can basically plot now relationship between U and the vertical axis, time in days here. So I have 1, 2, 3 values. Well, okay, they may be sufficient. So now I'm after 90%, so I go horizontal, come vertically here, and this will give me the solution approximate being 155 days approximately. So that's a straightforward substitution in the equations as long as you know the meaning of each term. So I should be able to see you in more videos. Thank you.